Hello again, welcome back to the Tech Project's Clean Air channel. Today I want to show you how you can calculate for a heat pump split system what the condenser heat duty is. Why is that important? Well, heat pumps, as you know, usually are designed on the cooling side to drop the inside temperature 20 degrees below what the outside temperature is. So if it is 80 degrees outside, the heat pump can pull the inside down to 80 minus 20, 60 degrees. If it's 115 degrees outside, like we've seen already in Las Vegas, Nevada, 115 minus 20, the heat pump can only pull it down to about 95 degrees. So as climate change progresses, the temperatures get higher, people are going to be bumping up to the limits on their HVAC condensers, and they're going to be calling you. You're going to have to go out there and check it out and see what's wrong. Well, I'm going to give you a plug and chug equation. I'm going to show you the hand calculations, and then I'm going to show you the formula at the end that you can just plug in the numbers real quick with a few field measurements and be able to determine if that condenser is operating at its maximum nameplate capacity. Okay. So we're going to use the BT 866A anemometer. It's very modestly priced at under $100, and we're going to use it and some other field measurements, and we're going to calculate the heat duty of this condenser. Now I'm going to show you my hand calculations. Yeah, I still do hand calculations, because when you use those canned computer programs, I've seen it happen in the chemical plants where a guy uses a canned computer program to design a reboiler for a distillation column, and you bring the plant up, you can't make production because that guy didn't understand the assumptions that are behind the black box called the computer. So when I use my hand calculations, I can always understand the limitations of my numbers because I know what assumptions I made, and I can evaluate whether those assumptions fit what I have out in the field. So I'm going to show you my hand calculations, okay? I always use the hand calculations. Here on the left, you see the condenser. It's sitting out here in the field. We're bringing in through the fan tubes, we're bringing in ambient air, and it's being heated up to a temperature. We call that T out. We call the ambient temperature T in. We're going to eventually get down here and use this heat duty equation right here, where Q, the heat duty, is BTUs per hour, is equal to the mass flow rate of air through the condenser times the heat capacity of air times the temperature difference, how much temperature this air picked up going through the condenser. Okay, and we're going to use the equation for the area of a circle because we're going to take our velocity measured by the BT866A anemometer. We're going to use that velocity, and we're going to multiply it by the area for flow, and that's going to give us a volumetric flow rate of air through the condenser that we can then calculate the mass flow rate of air, and we'll be able to calculate this heat duty for this condenser out in the field. Now, the area for flow is going to be, here's your shroud here. Okay, so it's going to be this area in the center here. Here's the hub for the fan. We're going to take the area of the shroud, and we're going to subtract the area of the hub where the fan is connected, where the fan blades are connected to the hub, because it's this angular space here is the area for airflow. Okay. The area of a circle, we got two circles here, the big circle with diameter D2, little circle diameter D1. The area of the circle is pi over 4 times the diameter of the circle squared. So that's basically all we're going to need to do this. There'll be a little details here and there we're going to have to figure out. Using the field measurements, we're going to use our anemometer. It is reading at 1202. The units here, you're going to have to use the same units I'm giving you today. If you're going to use that equation, I'm going to show you at the end. I'm going to develop a plug and chug equation at the end. And you're going to have to use my units if you want to use that equation to get the right answer. But it's going to be in feet per minute, the velocity of the air coming out of here. It's in feet per minute. So we multiply this velocity times this angular area, and that'll give us a volumetric flow rate in cubic feet per minute. Okay, so that's what we're going to do here. So the area for flow is going to be equal to the area of the shroud. That's the big area here. Minus the area of the hub. Here's the area of the hub here on the left. So the area of a circle is pi times the diameter squared of the shroud minus pi over 4 times the diameter squared of the hub. Factor out of pi over 4, and that leaves us inside the parentheses with the 2 diameters squared, the difference between the 2 diameters squared. Okay. So by tape measure, we find that D2 is 2.5 feet, and we find the diameter of the hub is at 1/2 foot. The volumetric flow rate then is the velocity that we measured from our BT866A anemometer and the area available for flow. The area available for flow turns out to be 4.71. Okay. And there's that 1202 that we saw before. So we multiply that 1202 feet per minute times square feet. It's going to give us a volumetric flow rate. That's our cubic feet per minute of air. Over here on the left, that's a cubic feet per minute of air that's being pulled through the condensers. In our heat equation, we're going to need the mass flow rate of air in pounds per hour. We have cubic feet per minute, and we're going to need to go to pounds per hour. To do that, we multiply the cubic feet per minute, which is 5663.8, times the density of air, which is 0.07 pounds per cubic feet. And that gives us 24,128 pounds per hour of air that's being pulled through the condenser, and it's being heated up from the outside temperature to this hot air temperature coming out the top of the condenser. So what is the temperature gain? We measure that. The temperature, ambient temperature is 95.27 degrees. The temperature of the hot air out the top of the condenser is 105.74. So the hot air, as it travels to the condenser, is picking up 10.51 degrees. That's that number right there, the temperature out minus the temperature in. Heat capacity of air, 0.24 BTUs per pound degree Fahrenheit. Do we have everything now? Yeah, we've got our mass flow rate of air, where we took our volumetric flow rate of air, converted it to pounds per hour by using the density and multiplying it by 60 minutes in an hour to get it to pounds per hour. There's our heat capacity of air. There's our temperature difference. And we get a number, 60,860 BTUs per hour. A 5-ton condenser, 5 times 12 gives you the BTUs per hour of that condenser. So 5 times 12, we have a 60,000 BTUs calculated roughly. Nameplate on this condenser is 60,000 BTUs. So this condenser is pretty much, this condenser indeed is maxed out. So you go see a customer, your customer says, hi, my AHC is not working right. You can go and you can do this quick calculation and give them the good news that, yeah, it's doing what it's supposed to do. The bad news is you're out of condenser capacity. Let's reduce this down to a more simple formula, a plug and chug formula. Here on the right side of the page here, we've got this condenser. You can see we're going to take the diameters, D2 and D1. We're going to have those in feet. Units are important. Temperature is going to be in degrees Fahrenheit. Our anemometer is going to be set for feet per minute for my BT866A. So you take your BT866A, multiply it by this factor at 0.803, the difference between the square of the diameters to get that. Remember the angular space there we had to get before? That's what this is. Our temperature difference, in our case, turned out to be 10.51. So we just plug these numbers in. There's our anemometer reading. There's our factor. There's our differences in the diameter of the hub versus the diameter of the shroud. There's our temperature difference. Again, we get 60,800 and some change BTUs per hour, which is a 5-ton condenser operating at maximum capacity. So if you go out and you do this calculation and you find that it's at 50% capacity, then you got to do some more digging around. You know, pull out your gauges and check around and see if you can find where you're losing that, why you're losing that cooling capacity. And if you indeed find this maxed out, then you can quote your customer a price for a bigger system. So that's all I have for you today. Thank you for joining in. If you find this information, find it useful, hit the like button, subscribe to the Tech Clean Air HVAC channel. Thank you for watching.